Section 10.4. In this section, we're going to look at adding, subtracting, and multiplying radical expressions, starting with addition and subtraction. When adding or subtracting radical expressions, you need like terms or like radicals. Then, as with any other like terms, you will use the distributive property to combine the numerical coefficients and keep the like term the same, as shown below. So from very beginning elementary algebra, you learned that if you were adding like terms and what made a like term was the variable piece was exactly the same, when adding like terms, it really ended up being a factoring problem. If you have a common factor, in this case x, you could factor that common factor out, and then you had a group of whatever was left. In this case, the 2 and the 5 are left after you factor the x out. 2 plus 5, of course, is 7, and then 7 times x gave you 7x. And then you quickly learned the easiest way to combine like terms was simply to add or subtract the leading coefficients, and then the variable piece just tacked on to the end of it unchanged. The same is true with radicals. In order to have a like radical, the radical piece has to be exactly the same, and if you're adding or subtracting, you need like radicals in order to add or subtract. And so just like with the example above it, you could think about it as a factoring out a greatest common factor problem. There is a common factor here of square root of x and square root of x, so if you factor that out, you're left with the group of whatever is left, in this case, again, 2 plus 5. 2 plus 5 is 7, and 7 times the square root of x is 7 times the square root of x. So the shortcut way to remember that is if you're adding or subtracting like terms or like radicals, simply do the math to the leading coefficients out front and then put the like radical onto the end of it unchanged. So let's look at some other examples and see what we get. For example, let's say I asked you to simplify 8 times the cubed root of x minus 15 times the cubed root of x. All right, in order to subtract those two, we do need exactly the same radical piece. We need like terms. Notice that we have that. We have the cubed root of x on both of those terms. So we can simply do the math to the numerical coefficients out front. 8 minus 15 leaves us with a negative 7. And then the like radical, which is cubed root of x, we'll just tack on to the outside. Negative 7 times the cube root of x. Now at that point you'd want to ask yourself, is there something I could do more that would give us a simpler form or simplest radical form? And the answer is no. In this case there's not. Our understood power of 1 is less than our index, and therefore that's simplest radical form. Okay, so let's simplify this problem. Let's look at the square root of 27 minus the square root of 75. Now, as written, those are not like radicals. The radical piece is obviously not the same. So what we're going to do with each of those is work with those, see if we can put them in simplest radical form, and then perhaps we'll have some like radical terms that we could then combine. So off to the side here, we know that 27 will break down to give us 3 times 9. And then 9 further breaks down to give us 3 times 3. Since this is an understood square root on both these radicals, we want factors that appear twice or that we can write as a square so that if we take the square root of them, we can pull out the base. Notice that 27 does have a perfect square in it. 3 times 3, or 3 squared, is 9. So looking just at this first radical, we're going to take the square root of 27 and rewrite that as the square root of 9 times the square root of 3. Or if you prefer, you can write that as the square root of 3 squared times the square root of 3. Okay? Either way, the square root of 9 or the square root of 3 squared will simplify and will give you a 3. And so that piece alone will give us, and I'm going to put it out over here, square root of 3 squared is the square root of 9, which is 3. And then we're left with the square root of 3 piece, which cannot be simplified any further. Okay, we're going to do the same thing with the square root of 75. If we take 75 and break it down, 75 is the same as 5 times 5 times 15, and then 15 breaks down further to give us 3 times 5. There is a perfect square in there as well. 5 times 5 is 25. 25 times 3 is 75. So to break down the square root of 75, we've then got the square root of 25 times the square root of 3, or the square root of 5 squared, if you prefer, times the square root of 3. Either way, the square root of 25 or the square root of 5 squared does allow us to pull out that 5. And then again, we have that square root of 3 that cannot be simplified further. Notice that by writing each of those terms in simplest radical form, we now have a radical piece that matches, so we have a like term. And so 3 minus 5 gives us -2, and the square root of 3 tacks on to the end of that for a final answer of -2 times the square root of 3. Let's look at this problem then. We've got the square root of 9b cubed minus the square root of 25b cubed plus the square root of 49b cubed. All right, again, as written, all three of those terms are unlike. The radicals do not match completely, and therefore you cannot add or subtract them since they're not like terms. What we'll do then for each of those terms is we'll try to simplify each of them to simplest radical form and then see if any two or perhaps all three of them will have like terms and we'll be able to add and subtract. So starting with this first term, 9 times b cubed, by the multiplication property of radicals, we can split that out. So we've got the square root of 9 times the square root of b cubed minus the square root of 25 times the square root of b cubed plus the square root of 49 times the square root of b cubed. Notice that 9, 25, and 49 are all perfect squares, so you can rewrite them as a square if you want to. For example, you could rewrite square root of 9 as square root of 3 squared if you prefer. Or if you just know those are perfect squares, you could skip the step where you write them as squares and just pull out the whole number. It's totally up to you. Because I'm running out of space on this problem, I think I'm just going to go ahead and skip the step where we write it as something squared and just do the math in my head. I know that the square root of 9 is 3. And then the square root of b squared, if we do that off to the side here, we're interested in the square root of b cubed. B cubed will not reduce with that b squared. 2 will not go evenly into 3, but 2 will go into b squared. And so we're going to rewrite b cubed as b squared times b to the first. That allows us to pull out one of the b's from the previous section, and then we're left with the square root of b in simplest radical form. The power is less than the index, so square root of b will not simplify further. So bringing that down here, square root of 9 is 3, square root of b cubed is b times the square root of b. Okay. Minus square root of 25 is 5. And here we have the square root of b cubed again. So that's going to be b times the square root of b. Plus square root of 49, I know, is 7, or square root of 7 squared, which is 7. And square root of b cubed again, is b square root of b. Now each of those terms is in simplest radical form. Also notice that our radical pieces all are now exactly the same, so we can do the math to the coefficients out in front. Watch the sign. So we've got 3b minus 5b plus 7b to simplify. 3b minus 5b is negative 2b. Negative 2b plus 7b is 5b. And then, in addition to that, we have attached our like radical, which is square root of b. So therefore, for our final answer, 3b square root of b minus 5b square root of b plus 7b square root of b gives us a final answer of 5b square root of b. Let's look at this problem. Let's look at the square root of 20x divided by 9 plus the square root of the entire fraction 5x divided by 9. Now, as written, those are not like terms. The radicand underneath the radical sign are completely different. So, starting with that first radical, if we split out that square root, we've got the square root of 20 times the square root of x divided by 9. And I know that in 20, if I break that down, there is a perfect square of 4. Okay, 4, of course, is 2 times 2. So the square root of 20 could be rewritten as the square root of 4 times the square root of 5, or the square root of 2 squared times the square root of 5, times the square root of x divided by 9, which then simplifies further to 2 square roots of 5 times the square root of x divided by 9. At that point, because I can't further simplify the square root of 5 and the square root of x, I'm going to rewrite that as a single radical, square root of 5x under one radical sign, just for simplification. Now, that is just that first term being simplified. So let's look at this second term and simplify it. So just looking at the second term here, we're going to break that square root sign out to cover both the numerator and the denominator separately. So we've got the square root of 5x divided by the square root of 9. Square root of 9 can be simplified. We've now got the square root of 5x over 3. And that term cannot be simplified further. Even if we split that square root sign individually out, the square root of 5x is the same as the square root of 5 and the square root of x, which is what we had down here as well, but that can't be further simplified, so I'm just going to leave that term like that. So now I'm going to combine those back into our addition problem. Here was our simplification of our first term. This is the simplification of our second term. And if you look at the original problem, they're being added. So we've got 2 times the square root of 5x divided by 9 now being added to the square root of 5x divided by 3. In addition to this needing like radicals to add, because they are fractions, we also need a common denominator. So at this point, we're going to need to build up our second fraction so that we can have a common denominator. So as with all fraction math, you're going to multiply top and bottom by 3 to get a common denominator. Then you'll add your numerators. So you've got 2 square root of 5x plus 3 square root of 5x, all divided by 9 now. And we do have like terms up top, so we can add the coefficients. And we've got 2 square root plus 3 square root is 5 times the square root of 5x, all divided by 9. There are no common factors that would allow us to reduce that fraction. Our radical already is in simplest form, and so that is our final answer for that problem. Now let's look at this problem. We've got the square root of 16 minus 5 times the square root of 10 plus 7. This is a subtraction and an addition problem. As written, none of the terms have like terms, so we are going to work with this as well. You might recognize that 16 is one of the perfect squares. The square root of 16 is the same as the square root of 4 squared, or the square root of 16 simplifies down to give us 4. Square root of 10, although you can break 10 down, 10 is 2 times 5, but neither of those factors appear twice. So the square root of 10 is in simplest radical form, so there's nothing we can do with this second term. 5 square roots of 10 is simplest form. And then, of course, we have this plus 7. Now, at this point, we do have a couple of like terms, which are just constants, so we'll simplify that. 4 plus 7 is 11, and to that we are still subtracting the 5 square roots of 10. These are unlike terms. You cannot subtract those, and therefore this is your final simplified answer. All right, let's look at the square root of 45 divided by 10 plus 7 times the square root of 5 divided by 10. The radical pieces do not match, so as written, you cannot add those, even though you have a common denominator. Square root of 45 and square root of 5 are unlike terms. So we're going to work with 45. 45 will break down. 45 is 5 times 9, and 9 is a perfect square. It's 3 times 3. So break 45 down, and we've got the square root of 9, or the square root of 3 squared, times the square root of 5, 9 times 5 is 45, divided by 10, plus 7 square roots of 5, which cannot be simplified, divided by 10. That now gives us, and I'm going to bring this up here, square root of 9 or square root of 3 squared is 3 square root of 5 divided by 10, plus 7 square roots of 5 divided by 10. Because we have a common denominator, we're going to add our numerator. 3 square root of 5 plus 7 square root of 5 over 10. These are like terms, like radicals. So do the math out front. 3 plus 7 is 10 square roots of 5 divided by 10. And since that's all multiplication and division, if you have a common factor, you can factor it out. And we're left with a final answer of positive square root of 5. Now we're going to look at multiplying radical expressions, knowing that when multiplying radical expressions, you're going to use the exact same rules that you used for polynomials. For example, you're going to use the FOIL method or the distributive property method or whatever other multiplication method for polynomials that you learned in the past will also work if the expressions have radicals in them. So let's simplify this problem. We've got the square root of 3 times the quantity square root of 3 minus 2 times the square root of 5x. Now you would agree with me that if that problem was something like this, 3 times the quantity 3 minus 2x, to simplify that, your first step would be to distribute that 3 and multiply it to each term in your polynomial group. That's your first step here as well. We're going to take that square root of 3 and we're going to distribute it and multiply it to each term in the group. So that's going to give us the square root of 3 times the square root of 3 minus the square root of 3 times 2 times the square root of x. Simplify where you can. Square root of 3 times the square root of 3 is the square root of 3 squared, or the square root of 9. Okay. Notice that that is going to simplify down to give us a 3. Over here, we've got 2 and the square root of 3 times the square root of 5x. I just changed the order there because the constant without the radical sign is normally written first, but that's all straight multiplication. Everything's being multiplied there, so you can multiply in any order. So now we have, if we bring that up here, simplify the square root of 9 or the square root of 3 squared, and we know that that's 3, minus 2 times, because these are like radicals, I can combine that under one radical sign. 3 times 5 times x is 15x. And then you want to ask yourself, could I write that radical piece in a simpler form? Are there any perfect squares in 15? And the answer is no, there's not. Our x is x to the first, so square root, you can't pull any x's out of there because your power is less than your index. You cannot combine these two terms because one doesn't have a radical and one does, so obviously the radical terms don't match. And so this is your final answer, 3 minus 2 times the square root of 15x. All right, let's look at this problem. Let's look at the cubed root of a minus 4 times the group the cubed root of a plus 5. All right, if that problem was written without radicals, if it was a minus 4 times a plus 5, you know that you would use some binomial multiplication method to simplify that. Like, for example, the FOIL method, or maybe you know the chart method. Distributive property also works for that. I'm going to use the FOIL method because I think most people remember the FOIL method better than maybe some of the other methods. So if we FOIL that out, F of course stands for multiplication of the first two terms. So that would be the cubed root of a times the cubed root of a, which is then going to further simplify down to give us the cube root of a times a, or the cube root of a squared. The outer product will be cubed root of a times positive 5, which gives us exactly that, plus 5 times the cubed root of a, which cannot be simplified further. Our inner product will be minus 4 times the cube root of a, so minus 4 times the cube root of a, or that's the same, of course, as just subtracting 4 times the cubed root of a. And the last two, minus 4 times a positive 5, gives us a plus negative 20, or just minus 20. Now look for like terms. There are some like radicals we could combine here. Those are both cube root of a to the first. So 5 plus a negative 4 is a positive 1. And 1 times anything is itself, so we're going to leave that coefficient of 1 off and just write the cube root of a. That's the same as 1 times the cube root of a. And then we've got minus 20 on the end. Now, all three of those are unlike terms. The radicals don't match, and in fact, the constant at the end doesn't have a radical. And therefore, this is as simple as that problem gets and is therefore the final answer. The cube root of a squared plus the cube root of a minus 20. All right, let's look at this example then. Let's simplify the square root of 2 times this quantity, the square root of 15, minus the square root of 35. This is a distributive property problem. We're going to multiply that square root of 2 throughout, which is going to give us the square root of 2 times the square root of 15 minus the square root of 2 times the square root of 35. Since those are like radicals, we can multiply that under a single radical sign. So the square root of 2 times the square root of 15 is the same as the square root of 2 times 15, which gives us the square root of 30, minus the square root of 2 times 35, which is the square root of 70. Now, those are not matching radicals. We can't combine them as written because it's subtraction. So, are there any perfect squares in either 30 or 70? If you break 30 down, 30 is 3 times 10, and 10 will break down again to 2 times 5. But notice that none of those factors appear twice, and therefore 30 has no perfect squares in it, so there's nothing we can do to simplify that. So let's look at 70. If you break 70 down, 70 is the same as 7 times 10. And again, 10 will break down to 2 times 5, but none of those three factors appear more than once, and therefore it also has no perfect squares in it. And this then would be your final simplified answer, since there's nothing more you can do, and you cannot subtract them because the radical pieces are not exactly the same. Now let's look at this problem. We've got the quantity 2 times the square root of 7 plus 3 times the square root of 5 multiplied to the quantity square root of 7 minus 2 square root of 5. That's a binomial times a binomial, so I'm going to choose to FOIL it. So if we multiply our first two terms together, we get 2 square root of 7 times square root of 7 will be 2 times the square root of 49, or 2 times the square root of 7 squared. Our outer product will be 2 times the square root of 7 times minus 2 square root of 5. 2 times 2 is 4, but because of the subtraction, we end up with a negative 4. And then square root of 7 and square root of 5 gives us square root of 35. Inner product will be these two terms here multiplied together. Positive times positive does give us a positive. We've got 3 times an understood 1 is 3, and square root of 5 times square root of 7 is square root of 35. Then our last two terms, which will be our 3 square roots of 5 and our minus 2 square roots of 5, positive 3 times negative 2 is minus 6, and square root of 5 times square root of 5 is square root of 25, or square root of 5 squared. So simplify and combine like terms where you can. Square root of 49 is 7, and so that 2 out in front will then multiply onto that. So we've got 2 times 7. Here we've got some like terms. So minus 4 and plus 3 leaves us with a minus 1, and that's minus 1 square roots of 35. And then here we have minus 6. Square root of 25 is 5, and so that will multiply on to the minus 6 that's ahead of it. Simplify. We've got 14 minus square root of 35 minus 30. And if we look at our constants there, 14 minus 30 does give us a negative 16. The minus square root of 35 is an unlike term, so we cannot combine that since it's subtraction, and that is our final answer. Final example. Let's take the square root of y minus 3x and take that quantity and square it. Remember that you cannot distribute that power of 2 to each of those terms. Okay? This is not equal to the square root of y squared minus 3x squared. You cannot distribute that power. Instead, write it out in expanded form. You've got the square root of y minus 3x times the same quantity, square root of y minus 3x. So like the previous example, you need to use the FOIL method or distributive property if you like that for binomial times binomial problems. I'm going to FOIL it out. So the first two terms, square root of y times the square root of y, does give us the square root of y squared. Y times y is y squared. Inner product, negative 3x times the square root of y is exactly that. Minus 3 times x times the square root of y. Outer product will be square root of y times minus 3x, which also is minus 3x, square root of y. And the last two terms, minus 3x and minus 3x, negative times negative is a positive 9. And then x times x, of course, is x squared. So simplify where you can. Notice that your power and your index match here, and your sign goes. So you're left with an y. So you've got a y here. These are like terms. So minus 3x and minus 3x is a total of minus 6x's. And then the square root of y tacks on. And then we've got plus 9x squared. All three of those that are left are unlike terms, so you cannot combine them since you're adding and subtracting. Therefore, your final answer would be y minus 6x times the square root of y plus 9x squared. Which brings us to the end of Module 16, Section 10.4. You should now complete the homework for Section 10.4, and when you have successfully completed the homework, proceed to the video for Module 16, Section 10.5.